Okay, I think we can start now guys, no? Medyo marami naman na tayo dito sa room. Tapos habol na lang yung iba and I'm recording this session as well, no? Just to be sure, record ko na lang din dito sa Google natin, sa Google Classrooms. Okay? So, for today, ang i-discuss natin is all about gating systems, no? And we have two topics. We've split the module into two, no? And both part 1 and part 2 kaya natin i-discuss today, no? So, let's begin, no? So, let me just open this. Nakikita nyo naman yung text on the screen. So, this was discussed in the introduction to introduction to metal casting, itong first four elements na to. So these are important elements when we talk about, and these are the main elements when we talk about metal casting, no? And gating systems in particular. So we have your pouring cup. So dito unang pumapasok yung metal natin. So this is a reservoir that initially receives the molten metal, and upon receiving the molten metal, it will flow out into the down sprue, or sometimes just simply the sprue, no? So the sprue is a vertical channel, and it delivers the molten metal into the gating system. The initial na when it comes down the down sprue, papasok siya dun sa sprue basin, sometimes known as the sprue well. So from the down sprue, ito, and I think I have an illustration dito, no? Let me just look for it. Ito siya. So we start with the pouring basin, or the pouring cup. Then from the pouring cup, usually yung shape na is something like this, no? Ito yung pouring cup, tapos meron siyang parang ganyan. Pwede siyang ganito. This is the usual shape. So if this is the pouring cup, it initially fills, tapos para ma-receive niya yung in a way, yung initial momentum nandito, such that hindi ka magkakaroon ng turbulent flow pagpasok dito. So eto siya, tapos it flows upward, or it fills upward. Then once it fills upward, pwede na siya mag-flow in a laminar fashion, no, papunta dito sa down sprue natin. So it can have this design, pero most designs pwedeng parang ganito lang, which is ito naka-offset nga konti, no? So pwedeng pumasok dito yung metal muna, tapos saka siya papasok dito sa down sprue. Some designs, lalo na pag medyo rudimentary lang yung yung kinakast nyo, pwedeng wala ng pouring cup at all. So pwedeng from the wari ganyan, diretso na siya. So you can pour directly into the down sprue. So the tendency lang pag ganito yung type of arrangement, no, is that yung down sprue pwedeng yung, lalo na pagka we're doing sand casting or some form of casting where the casting molding material is easily eroded, pwedeng itong parts na to may-erode siya due to the turbulent action ng pag-pour ng molten metal pasok dito sa And this happens quite a lot, no? And when we did experiment sa MetE150, usually nagkaka-incomplete casting dahil nag-collapse yung down sprue, tapos hindi na completely filled ng molten metal yung cavity natin. Okay, so kaya it's it's very important to add a pouring cup, no, to ensure na laminar yung flow natin. Okay? So from the pouring cup, papasok siya dun sa down sprue. So the down sprue is a vertical channel. Tapos to absorb or to cushion the momentum of your down sprue, because we know that from free fall magkakaroon siya ng, so dito velocity equals 0, no? So parang it's a smooth flow muna, velocity equals 0, and as it goes down, it gains momentum, or it gains velocity, because it's technically a free fall na action to, no? So from here to here, mas mataas na yung velocity niya. So once it reaches this portion, to cushion the momentum, pwede nating lagyan ng tinatawag na sprue basin, no? And sometimes this is known as a sprue well. So the sprue well just absorbs the momentum, or it slows down the momentum of the liquid metal para pagpasok dito sa runner, magkakaroon siya ng laminar flow ulit. Okay? So, dito, papasok siya from the sprue basin, pwede siyang pumunta sa runners, and then from the runners, papasok siya sa in-gates. Okay? So, there are systems wherein wala ng in-gate, no? So, for example, pwede ring, kung simple, so super simple lang yung system, pwedeng down sprue, then it enters the runner, tapos yung runner mismo, siya na rin yung gate. So, gates being the channels that directly feed the casting. No? So, for example, if this is your casting, this is your sprue, pasok siya dyan, this is your runner, which also acts as your in-gate. No? Papasok dito sa casting na to. Okay? So, we have, eto na siya, no? So, this is your, nandito ka na sa runner, tapos papasok siya sa in-gate, and we want to make sure that when it enters the gate, it enters in a consistent na, na flow rate para yung casting natin, it will fill appropriately and hindi turbulent yung flow such that ma-erode yung mga mold walls na to. Kasi once na na-erode, kunwari, masyadong mabilis yung pag-enter ng metal natin, pwedeng dito sa part na to, na-erode siya. And kung na-erode tong portions na to, mangyayari is, yung final product natin will have some defects, no? Doon sa portions na to. So, baka kailangan nyo i-post-process or totally unusable yung final product natin pag ganun yung nangyari. Okay? So, there are other, mga special designs. So, for example, you can also have a vent. So, a vent is just parang sila yung additional channels that relieve any buildup of gas pressures. Kasi when we are casting our metals, usually hindi maiiwasan na may retained, lalo na pag, for example, you're using green sand, no? So, meron kang retained moisture, and this moisture, when in contact with metal, they evaporate, no? And the evaporate could be the evaporated gas could build up pressure and pwedeng mag-collapse yung mold mo, no? Because of that build-up of pressure. So, para ma-relieve yung pressure na yun, you can add vents, no? And sometimes, ang ginagawa lang nila, lalo na pag sand casting siya, kunwari, ito yung sand casting, no? So, this is totally encased in sand. Tapos, ang ginagawa lang ng mga casters is, they just poke a stick or a long shaft, no? Which is parang thin shaft lang. Tapos, stick lang nila papunta doon sa mold cavity, producing parang essentially a vent, no? So, pwedeng they just poke multiple holes doon sa which creates the vents. Okay? Tapos, you'll also notice na meron tayong itong runner extension. Ang runner extension is just a way to ensure na yung first metal mo, we call it as the first metal, no? Yung first metal, usually, ito kasi yung maraming impurities, no? Kasi when we're casting, ang unang pumapasok is, if for example, ito yung or melting, this is our melting pot, no? And it's filled with metal. Usually, yung impurities mag-fill kasi dito sa sa top portion. So, yung unang nakakast or unang napupur na metal is actually full of impurities. So, yung impurities, ang action lang ng runner is that since it's running towards this direction, makakat siya dito sa runner extension natin. So, this runner extension, nandyan yung mga impurities natin. Tapos, once na fill up na siya, papasok na dito yung clean metal natin. Okay? Tapos, there's another term here, no, known as itong choke area. And this is a very important concept, and will actually be, or our calculations will be mainly focused on finding the choke area, no. So, the choke area is just the main control area for effective metal flow. So, this essentially dictates how the metal is being distributed into the mold cavity. Okay? So, ito, in this diagram, no, ito yung actually yung choke area. It is the area at the bottom of the sprue. So, kung gaano siya kalaki or gaano siya kaliit, it dictates kung gaano ka bilis or gaano kadaming metal ang nagpo-flow into our casting. Kasi if you make this large, then you have essentially a large na volumetric flow rate, no? If you make it small, then regardless kung gaano kalaki yung mga runners and gates na to, it will always be controlled by this initial na control area na to, which is the choke area. Okay? Malinaw ba yon? Does that make sense? Itong si choke area? Malinaw? Okay, thank you, Riquel, for the confirmation, no? So I hope that makes sense, no? Kasi all of our calculation will hinge upon this concept, no? Na the choke area being the main control area. By controlling the area, we control the distribution of our molten metal into the mold cavity. Okay? Okay, so the first calculation na gagawin natin is yung pouring time, no? So notice na si pouring time is different from your solidification time, but we'll use the same use the same notation T, pero to be accurate, pwede rin ang gawin nyo is TP, which indicates the time for the pouring time as opposed to your TS for solidification time. Okay, but you can also use T lang, no? So the pouring time T is a function of your is a function of three factors, no? So the three factors are yung fluidity factor, which is a material na property, no? Then we have the apparent thickness of the casting, and we have the weight of the casting. So these are the three factors that can affect the pouring time. Okay, so through several studies, no, again mainly done by NRL to, but there are other contributing na entities that have made these empirical equations I'll show later. We have this a few empirical equations now, and these are just some of them. So ito, we have one for steel where the pouring time is just equal to the material constant K, or the fluidity factor K, multiplied by the square root of the casting. So square root of the weight of the casting. So the weight is should be in pounds, and I think all of these equations now, they require that your weight should be in pounds for them to work. Tapos yung fluidity factor niya is equal to 2.4435 minus 0.3953 times the logarithm of the weight of the casting. Okay? So most of this is just plug and play, no? You just need to know the equation, tapos i-plug in nyo yung depending on what is asked, no? Pwedeng yung fluidity factor K, pwede ring it could also be yung weight of the casting. Ito dito sa ductile iron, you need to input the apparent thickness of the casting, no? So the equation is 0.5 plus T times square root of the weight of the casting, again also in pounds, and it's a piecewise function, no? So depending on the weight, magbabago yung form, yung itong square root na to. So it could be a square root, pwede ring cube root, or a quadratic root, no? So if it's up to 800 pounds, then we use square root. Pagka 800 to 10,000 pounds, then you use cube root. Tapos pagka if it's beyond 10,000 pounds, then we use the fourth root, no, of the weight of the casting in pounds. Okay, so we have here the apparent thickness should be in thickness as well. So pounds siya, tapos thickness din. So we are for these equations, no, gumagamit siya ng British units, no, or yung imperial units. Okay, so itong apparent thickness, this is in general, ito lang yung parang no, yung average thickness ng casting. So if you have, for example, ganito, if it's a casting with one thickness, then we can just say that the thickness is equal to the thickness of the casting, so apparent thickness. But if we say, for example, meron tayong kunwari ganyan, something like that, then what we do is we can use a weighted na average, no, for this thickness. So for example, if this spans a length of, let's just say L1, tapos ito spans a length of L2, and this is thickness 1 and thickness 2, Then we can use an average, no? So we can do something like um, L1 T1 plus L2 T2 over L1 plus L2. This is our apparent thickness. So it's a weighted average lang siya. Okay? But in most cases, binibigay naman yung ano no, yung apparent thickness, no. So this could also be just looking at the dominant na thickness. So for example, if you have a thickness kunwari ganyan, T, tapos meron kang small appendages dito and another appendage dito, then we can just say na yung apparent thickness niya is this large casting over here. So another, kung kunwari may appendage pa siya na ganyan, then the apparent thickness is just the dominant thickness, which is etong thickness na to. So pwedeng hindi na natin i-consider tong appendages na to, no. Okay? So usually for this MetE177, no, usually binibigay na namin kung ano yung apparent thickness ng casting, no. Unless magbibigay kami ng parang equation so onto how to solve the apparent thickness. So ganun. Pero yung problems na binigay namin dito and the worksheet, binigay na namin yung apparent thickness ng casting. Okay? Then we have for copper alloys. Copper alloys is just T times Tp, or the pouring temperature, is just equal to the fluidity factor multiplied by the cube root of the weight. Again, weight is in pounds. Tapos K will depend on the type of system or alloy na ginagamit natin. So here is a table na ano no. So we have a top gating, we have bottom gating, we have if we use a brass na alloy or if we use a thin bronze na alloy. Okay? So if it's pure copper, ito lang yung gagamitin natin. But if you use an alloy like brass or bronze, then we can use these two values here. Okay, then we have your gray cast iron. Sometimes it's abbreviated as GCI, no? So in the industry, they just call this as GCI. So gray cast iron is again a piecewise function, no? So meron tayong it's similar to the ductile iron formula, wherein meron kang mga limits, tapos nagbabago yung etong square root na to. So pwedeng square root, pwedeng cube root, pwedeng fourth root, no. Okay, so it's up to 1,000 pounds, you use square root. If it's 1,000, if it's between 1,000 and 10,000 pounds, then you use cube root. Because if it's over 10,000 pounds, then you use the fourth root of the weight. Again, in pounds ulit si weight, no. So dito, we have fluidity factor as well as your apparent thickness, no. So the formula is fluidity factor multiplied by 0.95 plus the apparent thickness T divided by 0.853 multiplied by either square root, cube root, or fourth root of W. Okay. Now to find this fluidity factor K, we usually have graphs, no, and the graphs for the gray cast iron uses a composition factor, no. Etong %C plus 0.25% ng silicon plus 0.5 the percentage of phosphorus. So once you compute for the composition factor, pwede mo nang magamit yung graph. So the graphs will look like this. We'll have dito, for example, if you have composition factor 3.4, then hahanapin mo lang yung temperature niya. And yung temperature niya is eto, no. Etong mga wait lang. Sorry. The way you use this graph is kunwari if you are given a composition factor of kunwari lang 3.4, tapos you are doing a pouring temperature of, let's just say 2,000, and this is in Fahrenheit pala to lahat, no? So let's just say 2,200 degrees Fahrenheit kunwari. Okay? So we use 3.4 projected upwards. Then we use a 2,200 Fahrenheit. So that's somewhere dito, no? 2,200 Fahrenheit. Pangit yung napili ko. So I'll just increase this, no? Gawin ko siyang 2,500 Fahrenheit. So if you use 2,000 degrees Fahrenheit, 2,500 degrees Fahrenheit, then we'll use something like this. So this value is in between these two lines, no? Etong line na to at etong isang line na to. So I'll zoom in, no? Parang ganyan siya. So it's in between the two values. Then we can just use we can do linear interpolation kung gusto nyo, or pwede rin mag-estimate na lang tayo, no? So this is between a fluidity of if we track this down, no, this is fluidity of, let me just use a different color, no? Sorry, mali. Nakakaduling siya minsan, no? So it's in between 14 and 16, tama? So ito yung two lines na to. It's in between 14 and 16. So we can use if we want to estimate, no, we can use a fluidity of just 15. So fluidity is often measured in inches, no? So kaya siya inches because this comes from your fluidity testers, no? Yung fluidity tester natin, this can actually be a study, no? This is I used to do this sa PBI dati when we were testing the fluidity of lead and its alloys. The way it works is, and let me just open new ano. So the way it works is, meron tayong parang pouring cup. May pouring cup tayo na parang ganyan. Tapos the pouring cup enters a channel. Tapos itong channel na to, it has a spiral, no? Mag-enter siya ng isang spiral. Parang ganyan. This is a fluidity tester. Tapos and so on and so forth. It can be of some great length, no? And I hope you can imagine this fluidity tester. So yung top view niya, para siyang ganito yung top view. So ito yung pouring cup, tapos merong spiral na ganyan. Again. And the way it works is, you measure how far your metal, liquid metal, reaches before it solidifies. So, pag pinuro mo kasi to, there comes a point wherein titigil siya because it has already solidified. So, you measure kung yung total length, and that is the fluidity in inches. So, kaya siya total length siya na na-travel niya before it solidified. So that's how your fluidity testers work, no? So dito ang formula dito sa for gray cast iron is that your fluidity should be the fluidity K is equal to whatever fluidity you get in inches, and you divide that by 40. Okay? So for the example na sabi ko, 'di ba, 3.4 na compositional factor tapos temperature of 2.5, ang nakuha natin is a fluidity of somewhere between 14 and 16, and we just estimate, sabi natin 15 inches na lang. So 15 inches divided by 40, this is now our fluidity factor K. Okay? So yun yung i-input natin dito sa K na to. Okay? So let's do some sample problems, no? So let's try to determine the optimum pouring time for a casting whose weight is 50 pounds and has an average section thickness of around 0.75 inches. So we are to calculate both for cast iron na material and steel na material. So it is taken that the fluidity of iron is at 32 inches. So binigay na dito, no? So we don't have to actually use the graphs. So dito, for steel, we can just input the formula directly, no? And the formula again is just T is equal to K multiplied by the square root of the weight in pounds, and the K is equal to 2.4335 minus 0.3953 times the logarithm of W. So we just plug and again sa pouring time, no, it's mostly plug and play lang. You just need to know the material, look at the equation for that material, yung pouring temperature equation for that material, tapos i-plug in nyo lang yung values na. Okay? There are also different types of this is an example of yung parang meron ka lang lines and you do you do interpolation para makuha yung fluidity, pero there are also, if you look online, no, meron ka ding mahahanap na iba't ibang fluidity graphs. So some of the graphs are parang nomograms sila, no? Or nomograms ba yung proper term? No, nomographs pala, nomographs. So, wherein meron kang, you can have something like, parang ganito, no? Pwede siyang ganyan, ganyan. Tapos, merong fluidity factor dito sa gitna. So, if you're familiar with, ano bang isang sikat na nomogram? Isang sikat na nomograph is yung Richter scale. Tama ba? Yung sa pag-measure ng yung impact, kunwari yung i-measure mo yung magnitude, tapos measure mo yung nakalimutan ko na. Pero sige, anyway, yung eto, the way it works is merong certain na kunwari magme-measure ka ng temperature dito on one end, tapos measure mo yung fluidity factor on one end, tapos gaganyan mo, tapos kung saan siya tumama dito sa sa graph, sa nomograph na to, yun yung magiging fluidity factor K niya. Parang ganun. Tapos pwede rin baliktad, no? Kunwari, if you're given a K value, tapos given ka ng composition factor, pwede mong i-predict kung ano yung optimum pouring temperature niya. Pwede rin ganun. So this can also be used for that. Itong graph na to, that can also be used for that. So for example, if you're given the fluidity factor, kunwari 28 daw ang fluidity factor, and you are given the compositional factor 2.6, then you just bring this up, tapos kunwari punta tayo sa 28, this is the 28 line, tapos tingnan natin our optimum pouring temperature for that scenario should be around 29, parang ganun, 2,900. So you can use this graph in many ways, no? And baka pwede rin naming ibigay yun as a problem, no? Yung how to what is the optimum pouring temperature temperature given a specific na pouring time. Pwede rin ganun siya, no? Okay? So, eto, input lang yung values. We are given 50 pounds, so we input W as 50, tapos we solve for this equation, and we should get the value 12.53 seconds. And this pouring time is important, no, because we will actually use this pouring time value when we compute for the choke area. Okay? So, eto, for GCI, we just use, since this is 50 pounds lang, so this is less than, ang limit data for GCI is 800 pounds, no? So if it's less than 800 pounds, then we use the square root of W. So that's square root. Tapos input lang natin yung W, and sabi daw the fluidity is of iron is 32 inches. So ang formula is yung fluidity in inches, divide natin siya by 40 para makuha yung fluidity factor. Okay, so that's why it's 30 over 40 plus 0.95 plus 0.75 over 853, which is just given in the formula, no? So we have 32 over 40, 0.95 plus 0.75 over 0.853 multiplied by square root ng casting weight, which is 50, which will give us 10.35 seconds. Okay? So again, simple lang ang pouring temperature is just looking for the equation, plugging that equation and solving it. Okay? Now we proceed to choke area calculation, and perhaps this is the most important na calculation when we talk about gating design, no? Kasi almost all of our succeeding na calculation will depend on ano yung nakuha natin sa choke area natin. Okay? So, the choke area is a function of multiple factors, no? So we have the weight of the casting, the pouring time, which we have already calculated, the density of the casting, and we also have yung isang hydraulic efficiency factor, which is like a correction factor lang, no? Yung hydraulic efficiency factor, because in most cases hindi kasi 100% magpa-flow yung material natin, no? So there is an efficiency factor involved. Then we just multiply it by square root of 2gh. So this formula, no, actually comes from your volumetric flow rate formula, which is Q is equal to VA. And I encourage you guys to try to solve this on your own, no? Pero just a preview, if you look at it, we can actually rearrange this, and this becomes A is equal to Q over V. Okay? where Q here is the volumetric flow rate, tapos V is the flow velocity of the fluid that we are measuring, no? And in this particular instance, the fluid is our liquid metal na kinakast natin. Okay? So in this case, si Q natin will actually just be, kasi ang definition kasi ni Q is the volumetric flow rate. So this is just actually equal to the total volume of the casting, kung ilan yung ikakast natin, tapos divided by the total pouring time. Tama? Kasi if we measure how much material is being poured divided by the total time that material is being poured, makukuha natin yung volumetric flow rate niya. Okay? So kaya if you look at this equation, ito actually siya, no? If you look at this, what is this? Weight over density. Weight over density is just volume, no? Kasi di ba, if you remember, density is just equal to mass over volume. Therefore, volume is equal to weight over density. So this is just volume. So that's volume over pouring temperature. Ito, we can equate this to volume over temperature. That is our Q. Okay? And ito, square root of 2GH, parang dinerive ko na rin pala para sa inyo, no? Pero anyway, etong square root of 2GH, ito actually ay, this is a free fall na equation, no? Tama? If you remember, if you have you have an object that is experiencing free fall, yung velocity niya at kunwari ito, it starts with at velocity equals 0 and it falls down. Then the height, if you know the height for which it is falling down, then you can determine kung ano yung final velocity niya at the end. And this is equal to square root of 2GH. Okay? So kaya doon nagaling yung square root of 2GH. Okay? So etong efficiency factor, again, because it's not in the real world, it's not 100%, no? So kaya mag-input tayo ng efficiency factor. Okay? So try to solve it on your own, no? Try to get the full derivation kung paano natin makukuha tong choke area calculation na to from just the flow rate equation Q equals VA. Okay? So first na i-consider natin doon sa equation na yon is yung effective metal head muna, no, yung H. So in general, yung H natin is just the sprue height, no, kasi ito yung effective na height na tina-travel ng liquid natin from the pouring cup when it enters our gating system. Okay? Pero there are some considerations that we need to take when we compute for the effective metal head. Okay? So first is, kung meron tayong tinatawag na top gate system. So a top gate system is where, if you look at again, yung choke area kasi natin is the bottom of the sprue, no? Ito yung area at the bottom of the sprue. So this is your AC or choke area. If you look at where the choke area is level, kasi where the choke area is essentially the same level as your runner or your runner and the gate system. Okay? So if you look at the choke area, it is level with if it's level with the top of the casting, then we call this as a top gating system. Okay, so this is a top gate. So if it's top gate, the equation is yung effective metal head, which is given as the capital H, is just equal to the sprue height, the total height of the sprue configuration, which is given as H. So etong sprue height na to, H, will include the pouring cup height, no? So etong total na to will include yung height ng pouring cup as well as the height ng sprue natin. Okay? Next is if we have a bottom gating system, no? So ang bottom gating system, as the name implies, is yung choke area natin, which is this case, ito, is aligned with the bottom of the casting. Okay? So if it's aligned with the bottom of the casting, then we need to use the effective head is equal to H, capital H, effective head is equal to the total sprue height minus minus the height of the casting divided by 2. So ito yung height ng casting natin. So kung wari ganyan, is the height of the casting. And if it's, kunwari lang, meron tayong casting na may ganito siyang assembly, no? Kunwari, we need to take the maximum height of the casting, no? Kasi, again, we are trying to fill the casting completely. Therefore, kailangan natin siyang yung head, the head kasi is, if you've already taken ES, ano ba, hindi ko alam kung anong ES sa inyo to, pero yung fluid mechanics na ES 15 yata siya. Sa time namin is ES 15, pero hindi ko alam kung sa ano na yung, nakalimutan ko kung ano yung equivalent ES nyo dito. Meron pa kayo, Riquel says 15. Meron pa kayong ES 15? Tama ba, Riquel? And others? Meron, okay. So, if you taken ES 15, then you know that yung head is synonymous with pressure, no? So, yung head kasi is the amount of pressure you need, parang potential energy you need para ma-fill out yung maximum required na pressure head. So, in this case, kung ito yung casting mo, kailangan ma-fill out mo hanggang dito. So, the C variable here is the highest peak of your casting. Okay, so if you have a top riser, and definitely kailangan natin i-fill out din yung riser, di ba? So if you have a top riser system, kunwari may riser pa tayo dito, if you have a riser here, then we need to consider our C here becomes the casting plus yung riser height pa. Because again, we need to fill out the riser. Because if we only consider C here, then posible na hindi natin ma-fill out yung riser head natin, or yung head needed, or yung pressure needed para ma-fill yung riser. So, hindi makaka-function yung riser, and we can have some shrinkage defect posible dito sa portion na to, because we didn't consider the height of the riser. Okay? So again, the formula is the effective head becomes the height of the sprue assembly, which includes the pouring cup, minus the highest point sa casting natin divided by 2. Okay? Now, if we were to use a mid-gate, so mid-gate means that the choke area, ito, which implies that the gating system, again, the gating system is almost always aligned with the choke area, no? Is equal to, or is in between the top gate and bottom gate. So, in between siya dito sa lowest portions, etong lowest and the highest portion. So, somewhere in between yung gate natin or yung choke area alignment. Okay? So, if that's the case, then you need to take into account this value here, yung P, which is the highest point minus the point where the choke area is located. And the formula becomes capital H, effective head, is equal to the sprue assembly height minus P squared over 2C. Okay? So, one thing we'll notice is etong equation na to is actually a general equation, no? Kasi if we, for example, if we did a bottom gate, then or if we did a top gate, for example, kunwari, kung top gate siya, then in that scenario, P is just equal to 0. Tama? So, if we input P equals 0 dito sa equation na to, we have H equals H minus 0 over 2C, which cancels this out. H is equal to H. Okay? So, which brings us back to the first equation, no? H is equal to small h. Tapos, if we use bottom gate, kunwari, ilagay natin siya dito, then P here is equal to C. Tama? So, this distance P is just equal to the casting height C. Therefore, kung i-input natin dyan, we have C squared over 2C, and the squared cancels. We will be left with the equation H minus 2C, which is, H minus C over 2. I'm sorry. So, it's H minus C over 2, which is exactly this equation, no? So, you can use this general equation, no? Kunwari lang, if you don't have any notes, no? Then you can just memorize this one equation right here. Ito lang si P squared over 2C, tapos lahat na ng configuration ma-derive nyo. So, if you have a top gating, whether you have a top gating or a bottom gating, then you can just derive it from this general equation na to. Okay? So, we're done with yung first, no? So, Okay na tayo dito sa effective metal head. Now we proceed with, this is given, no? Si casting weight is given. Density can also be given. Tapos pouring time, we've already calculated it. Tapos acceleration due to gravity, excuse me. Acceleration due to gravity is a constant. This is also known. So kulang na lang natin is itong hydraulic efficiency factor para ma-solve natin si choke area. So the hydraulic efficiency factor is it's a complicated formula, and it's a very rigorous na formula, no? So if you look at it, it involves this equation, which is just 1 over square root ng 1 plus, we have yung loss coefficient, so itong K1, K2, and depending on how many changes, downstream changes you have, then you can have multiple na K values or loss coefficient values. Okay? Then you have your areas. Etong A na to, this is just the choke area, no? Etong A. Etong nasa taas, capital A is the choke area. Etong nandito. Tapos yung A1, A2, and I'm sorry. Scratch that, no? Etong A na to is the upstream na area. Ito upstream. Tapos ito yung downstream. Okay? So for example, an example is kunwari, let's look at the first, no? Nope, nandito siya. Okay, let me just look for it, guys, na. Ito kunwari. So this is kunwari, pumasok yung metal from this point to this point, then this area here is a downstream value, and kung saan siya nanggaling, it's an upstream value. Parang ganun. So let's take another case. So for example, this is the runner, so it has an area here. If the metal enters this one, then pasok siya dito sa gate na to, so there is a change in area, tama? So that change in area accounts for a downstream value. So ito yung downstream natin, which is the gate, tas ang upstream natin is the area from which it came from, which is the runner. Okay? Nagigets ba yun? So let's do a kunwari lang, this is your sprue, tas ito yung choke area niya. Then from the choke area, magra-run siya into two sections, no? Kunwari ganyan. It runs into a runner. So yung first area niya is pwede siyang pumasok dyan, or pwede rin siyang pumasok dito. So in this case, dalawa yung changes niya, no? So we have yung choke area AC, tas kunwari runner area to AR. Then you need to account for, doon sa equation natin, meron tayong 1 plus, yung K1 natin is yung first A over AR, tapos meron din tayong K2 A over AR again. Parang ganun. And i-account natin lahat ng dadaanan ng metal. So for example, ito, kung mag-change siya, magbe-bend siya, kunwari na ganyan. If the runner bends, so if we look at, kunwari, a top view, kunwari. If you look at the top view, tapos sa top view, kunwari lang, ito yung pouring cup, no? And the choke area, nandito yung choke area. Tapos nandito yung runner natin. Tapos yung runner natin, nag-bend siya ng ganyan. Kunwari. Tapos equal lang yung area na. So the area here is just, ito yung area ng runner. Tapos meron tayong area ng runner ulit dyan. And again, this is top view to, top view. So ito, papasok siya dyan. Pero since there is a channel change, no? Kasi directions are also considered as change. So hindi lang area change, no? Pwede ring directional change. If there is a directional change, then there is a loss coefficient associated with that directional change. Pero since is equal lang yung area, then ang gagawin natin is yung i-add natin na K3, equal lang siya sa K3 times 1. So it's 1 because yung area niya is just AR over AR. Hindi naman nagbago yung area kasi. Kasi yung upstream niya is the same as the downstream na na area. Okay, so I think I'll have to reword this, ano no, i-reword ko lang yung equation kasi parang ang sabi ko ata dito dun sa coefficient, wait lang ang sabi dito is yung A is the choke area, pero this is not necessarily true, no? So this is supposed to be the upstream na cross-sectional area. Okay, I'll make the necessary corrections later class, no? Okay, so here are examples of loss coefficients, no? So we have kunwari sprue entering from pouring cup that has an associated na value loss coefficient of 0.75 if it's a sharp turn, pero you can do filleting, no, which entails a round turn, and that reduces the loss coefficient to 0.2. Okay, so if you have a bend of sprue into runner, so that's saying na kunwari ito yung down sprue natin and it bends to enter the runner, then it entails a loss coefficient of 2. Pero kung rounded yung corner mo, so for example, if I round this, okay, i-round ko ng ganyan, then I can have a loss coefficient of only just 1, no? Okay? Tapos, if it's a right angle bend in the runner, so kunwari, ito yung top view ng runner, yung similar sa ginawa ko kanina, so ito yung choke area, tapos it enters a runner, tapos nag-bend yung runner mo ng ganyan. Then if it's a cross-sectional area, then it entails a sharp turn of 2.0 pero 1.5 pagka round. Tapos kung round yung cross-sectional area, then it entails a sharp turn of 1.5 tapos and 1.0 pagka round naman yung bend na yon. Okay, so there are multiple sobrang daming ways wherein you can have a loss coefficient, tas kailangan nyo lang i-account lahat yon doon sa natin sa hydraulic efficiency factor C. So one dilemma here, class, no, if you notice, is that if you look at it, di ba we are trying to solve for the we need this coefficient C para ma-solve yung choke area. That is what we're looking for. Pero si C mismo, kailangan mo yung choke area para ma-solve siya. Kunwari ito, yung upstream natin. This is the choke area, no? Tapos kailangan din yung area ng runner, which is yung runner area is dependent on the choke area. So the runner area, in-gate area is all dependent on the choke area. So how can you solve something na para siyang circular reference in a way? So the way we can circumvent this problem is we use the gating ratio, no? So we establish the gating ratios first. A gating ratio is just the ratio of your AC, AR, and I or G, no? In-gate or gate. Okay? So ito, usually these are empirical values that are known to give the best results. So we can have, kunwari, if you have something like 1:3:3, this is saying na yung area ng choke, yung choke area mo is equal to 3 times or yung area ng runner mo, yung total area ng runner mo is equal to 3 times the area of the choke. Okay, so with that in mind, pwede mo actually ma-solve na to, no? So for example, if you are entering if this is a choke area, and let me just zoom, no? Kunwari lang, this is a sprue, tapos ito yung choke area niya. It is entering a runner, para ganyan. And we know that the gating ratio is 1:3 for choke to runner. Then ito, if it's a single runner, no, then yung 3 natin, yung area ng runner na to is just 3 times the choke area. Okay? So, pero kung if it's a symmetrical, kunwari ganyan siya, and it enters 2, kunwari AR2, AR, there's AC, then your your AR here becomes AR is equal to 3 times, AR is equal to 3 times the choke area divided by 2. Kasi again, yung gating ratio natin is the area of the choke, the ratio between area of the choke, the total area of the runner. Again, total to. Ito rin, total din to. So, depending on how many runners you have, how many in-gates you have, kailangan mo i-divide yung total na yon by that same number para makuha yung individual na, for you to get the individual values for the runners and the areas. Okay? Malinaw ba yon? So, back to the point dito sa coefficient, hydraulic efficiency factor, pwede mo actually ma-solve na tong values na to without actually computing for choke area in the first place, no? Kasi we can use gating ratios lang. So, for example, ito, it enters a bend. Kunwari, yung first natin na change na in-account, upstream to downstream change is, kunwari, choke, sprue into runner. So, kung sprue into runner, that's, let's just use sharp turns, no? So, if it's a bend of sprue into runner, and we have one runner lang, and we have a gating ratio of 1:3, kunwari, then, etong value na to just becomes 2.0. So, this becomes 2.0. Tapos, etong value na to becomes 1 squared over 3 squared. Tama? Because this is the choke area, the upstream area divided by the downstream area. Cross-sectional area, I should say. Okay, so without solving for choke area, na-solve na natin tong, or may values tayo para dito sa, sa loss coefficients na to. Because we know, just because we know the gating ratios. Okay? Okay. So, that is the most rigorous way of trying to solve for the efficiency factor, no? Pero in most cases, hindi masyado siyang matrabaho for just solving the coefficiency factor. But we can just use tables that look like this, no? Ito naman, this is the efficiency coefficient based on the various types of gating systems. So, ito kunwari, if you have a single runner entering a runner, then we can just use a coefficient factor of 0.9 if tapered yung sprue natin. Pero if you have a straight sprue, so a tapered sprue is when you have something like this, no? Kumbaga yung top, and we'll use this value later on, no, pag nagsosolve na tayo. We have a top na area, and we call this as the choke area. This is the choke area. If the top area is different from the choke area, then we have what we call as a tapered screw, and we can actually also kaya natin compute tong angle, taper angle, no? Pero more on that later. So, if it is tapered choke sprue, then your efficiency factor C, whole C na to, no? Yung C value mismo, hindi yung loss coefficient value na K sub N. Ito, C na talaga yung nasa-solve natin. So, we have 0.9 lang siya. If you have two runners with multiple in-gates, but there are no bends in the runners, then you can use 0.9 again. If it's two runners with multiple in-gates, and there are 90-degree bends in the runners, then we can just use 0.85. A good rule of thumb is, kunwari lang, you don't have access to this table, tapos kailangan mo ng value for C. Good rule of thumb is, just use a C value of 0.85. Okay, so this is a rule of thumb lang siya, no? Pero if you have access to different tables that can give you a more accurate na result, then you can use those tables, no, para mahanap yung, or para ma-account mo yung changes doon sa gating system mo. Okay, so let's try this sample problem. So we are to determine the choke area of a gray cast iron whose casting weight is 49.125 kilograms, and we are to use a fluidity of 22 inches. Okay? I'm sorry, hindi dapat 2 kilograms, no? Sorry, kilograms. That's correct, no? So, okay. So, we use two runners with multiple in-gates, and we have 90-degree bends in the runners. Tapos, ito yung mga conditions, no, sa gating design na to. We are using two runners, multiple in-gates. Tapos, 90-degree bends in the runners, and we are to use a top gating system with a sprue height of 100 millimeters. So it's not indicated, no? So we'll just assume na itong sprue height na to already includes the pouring cup height. And we are given the density of the metal in its liquid form, which is 6.98 times 10 to the negative 6 kilograms per millimeter cube. Okay, so first we calculate the pouring time. So the pouring time can be calculated from the GCI equation mentioned earlier, no? So it's equal to K, which is just the fluidity in inches divided by 40. So this is the K value, plus 0.95 plus the ano nga ulit to? This is the apparent thickness. Wait, let me double check last, no? Double check natin yung GCI equation. GCI is the apparent thickness divided by 0.853 multiplied by square root of W. Okay? So, dun sa ano natin, equation, okay, sorry. Because this is apparent thickness, saan nagsanabi yung ano? I forgot to mention the ano, no? So, sorry. Meron pa lang isa pang condition dito that the apparent thickness is equal to 50 millimeters. Okay? So, since 50 millimeters siya, kailangan natin siyang i-convert into inches, which is 25.4 millimeters. Kaya may 25.4 dito. So, the height of the the apparent thickness of the casting is 50 millimeters, and we need to convert it into inches. That's why we divide it by 25.4. Tapos divided by this is just a constant of 0.853. Tapos since the casting weight is lower than 800 pounds, 1,000 pounds. Tama ba? 1,000 pounds yung threshold niya. Look at it. Tama? It's 1,000 pounds. It's lower than 1,000 pounds. Therefore, we use square root of W lang yung gagamitin natin. Okay? So, it's square root of W. And notice na i-multiply natin siya by 2.2 because, again, dapat naka-pounds kasi yung weight natin. So, this is in kilograms times 2.2 gives us pounds. So, this 2.2 pounds per 1 kilogram. Tapos, ito, this is 25.4 mm per 1 inch. So if you divide it, we get a number of inches, no? Okay? So we solve for the pouring time, which is 18.63. Tapos, we know that a top gating is to be used. Sabi kasi dito, top gating is to be used. Sprue height is 100. Then, our effective head is just equal to the sprue height, which is 100 millimeters lang. Okay? Tapos sabi dito, two runners with multiple in-gates. Tapos may 90-degree bends. That's two runners, multiple in-gates. Ito pala siya. Two runners, multiple in-gates. Tapos may 90-degree bend tayo sa runners. So we use based on this table, we should use a 0.85 na hydraulic efficiency factor. So hindi sinabi dito kung ano yung type of sprue, no? Kung straight ba siya or tapered. Pero if it's not mentioned, we always want to use tapered sprue. Later, I'll explain kung bakit importante na tapered yung sprue natin, no? Okay? So if it's not specified, we always want to use a tapered sprue. Okay? So from there, pwede natin input yung equation natin. So we have 18.63. Thus, this is the casting weight divided by the density. And again, we use the density of the of the liquid metal kasi again we are doing this, ito kasi is based on the flow rate equation, which entails na yung volume na pumapasok na metal is the volume of the liquid metal. Therefore, we should use the liquid metal density as opposed to the solid metal density. Okay? So we use 49.125 divided by 6.98. Tapos from there we multiply this by the coefficient factor 0.85. Thus this is square root of 2gh, which is again this is our velocity term, no? So we'll use 9,800 mm per second squared for the g value para puro naka mm siya. So konti na lang yung or para yung final answer natin will be in millimeters na. Okay? We'll multiply it by the effective height h, which in this case is just yung sprue height natin, small h. Okay? So that's 100 millimeters. And if you do the evaluation, we should get the choke area of 317.457. Now, if we do this, ito yung choke area natin, no? And for example lang, ang sabi, we have a circular sprue, then we can actually compute for the dimensions of the sprue din, no? So, we just, area is equal to pi over 4 d squared. Pwede natin makuha yung d. Tapos, kung sinabi naman, if you use a square sprue, kunwari, we can also use a square sprue, no? Kunwari ganyan. This is an example of a square sprue. And meron siyang square cross-sectional area, then kunin lang natin yung square root ng value na to get the dimensions of that square sprue. Okay? Okay. So that's choke area. Now, we proceed with gating ratios, and gating ratios medyo mas simple na lang to, no? Ito lang talaga yung bulk ng difficulty ng when we talk about gating systems. Before we proceed to gating ratios, meron bang questions so far on the choke area? Okay ba tayo? Okay. Pwede bang i-chat nyo yung kung meron kayong questions or kung good tayo, proceed tayo sa sa gating ratios. Okay lang. Okay, Rebo. Thank you, Rebo. Yung iba? May tanong ata si Riquel. Pwede pa ulit yung aling part, Riquel? Yung saan galing yung 50 over 25.4. So again, hindi ko lang kasi nasama sa sample problem, no? Pero the sample problem should have yung apparent thickness niya should be equal to 50 millimeters, no? Tapos kaya siya 50 over 25.4 kasi dun sa pouring time equations natin, apparent thickness should be in inches, tapos yung weight should always be in pounds. So kaya yung 50 millimeters na apparent thickness, divide natin by 25.4 to get the apparent thickness, which is in inches. Okay? Nasagot ba yun, Riquel? Yung tanong mo? Okay, thank you, Riquel. Yung sa iba? Silence means yes, siguro no. So I'm assuming na nakuha nyo. If in case meron kayong maisip na tanong, for example, later on, while you're reviewing the module, if you have any questions, just contact me or Juan, and we'll be happy to answer your questions. No? Okay? Okay. So, proceed tayo sa gating systems, no? So, let me just open gating systems. Okay. Okay. So first, ito muna tayo. Oh. So ito, when we're computing for down sprue na dimensions, we need to take into account kung ang important lang dito is if meron tayong tapered or straight na down sprue. Okay? So kung straight lang yung down sprue natin, then kung ano yung if we have a straight down sprue, no? So kung ano yung mako-compute natin na AC dito sa baba, then it's just equal to whatever we just say AT to, no? A sub T. So A sub T again is the area at the top of the sprue, just below the pouring cup. So if, for example, if we have a pouring cup like this, kuwari ganyan, then the area at the top is just equal to the area, the choke area at the bottom, which we have computed now based on the equation from the previous module. Okay? Pero if we are considering a tapered na sprue, which is the more convenient or the more effective na type of sprue, no? Then we need to calculate the etong AT na to. Okay? So why is it necessary to taper our sprue is because of free fall, no? Because we know that from this point, if, for example, if we start at this point V is equal to 0, no? Tama? Then if it goes down, as it goes down, it increases in velocity. Tama? At this point. And we know that at this point to this point, lalong mag-i-increase pa yung velocity natin. Tama, no? So, if we want to maintain the volumetric flow rate, so we want to maintain the volumetric flow rate, no? Because if hindi equal yung volumetric flow rate, kunwari, if there is a certain volume that passes through this area, tapos it enters a smaller area, kung hindi equal yung volumetric flow rate, then ang mangyayari is we can have tearing, no, dito sa fluid flow natin. So posible na either kunwari mas konti ang volumetric flow rate dito as opposed to dito. So pwedeng if that's the case, then pressurized siya, no, parang ganun. So it's pressurized kasi mas maraming pumapasok kesa lumalabas dito, and therefore posibleng mag-collapse or mag-explode tong cavity dito, yung mold wall dito. Tama? Yung surrounding mold wall dito will explode because you are entering more liquid than the liquid that is exiting. Tama? Tapos kung ang opposite naman is, for example, is if you are exiting more liquid metal than you are entering, then ang mangyayari is ang mangyayari is it can aspirate air, no? So meron kang tinatawag na air aspiration. So posible na air will come in with the liquid metal, tapos yung air na yon will be trapped in as porosities. So mag-entrap ka ng air, therefore yung pumapasok dito is a liquid metal that has entrapped air that can cause porosities in your final product. So our goal is dapat yung pumapasok doon sa taas dito sa AT natin is the same volumetric, yung flow rate niya volumetrically is the same as yung lumalabas dito sa AC para ma-ensure natin na meron tayong laminar flow. Again, I'll always talk about dito, no, and it helps if you've already taken ES15, no, because you know the difference between laminar flow and turbulent flow. Essentially, what I'm saying is, if hindi constant yung flow rate given as Q, no, if hindi siya constant across the entry and exit point, then you will have turbulent flow. If constant siya, then you'll have laminar flow. Okay? So, a goal natin is equal yung volumetric flow rate. Therefore, ang volumetric flow rate equation kasi natin is VA. So, we're just saying if you want this to be constant, then you just need V1A1 equal to V2A2. And this is a very familiar equation, no? If you've taken ES15, sobrang daming formulas that come from this basic constancy of volumetric flow rate, no? Okay, so in our case, ATVT is just equal to ACVC. Okay, so from here, ATVT equals ACVC. If we want to measure the velocity at AT, then we just measure the amount of free fall na in-undertake nga. Tama? Kasi, again, from free fall is just square root of 2gh, where h here is the height from which it is falling, no? Or the distance that it has fallen up to that particular point. So dito sa AT, sa itong AT natin, it has fallen a distance of h. In this diagram, no, it's a small h. Pero note that this is different from yung h dun sa ano natin, top gating system. So to differentiate, I'll just say na I'll take this distance as the height of the pouring cup. So pwedeng, let's just use HP, no? HP. So this is HP, and we'll just say HS to, and this is HT, which stands for total. So total, height of the pouring cup, height of the sprue. Okay? So dito, see at this point, particular point here, the velocity of the liquid is equal to square root of 2GHP. Tama? Tapos at this point, it has fallen a distance of HT. Tama, no? It has fallen a distance of HT. Therefore, yung speed niya is square root of 2GHT. Okay? So, if we do the calculation, then we can get something that looks like this. So, the area at the top is just equal to AC over square root ng HT, which is area at the top, divided by the H. And in this case, yung small h natin is yung height of the pouring cup. Okay? So from eto na-compute na natin earlier, no? If we multiply it by this ratio, by the square root of this ratio, then we get the area at the top. And this is very you can also find this in our this equation actually has a parabolic na graph, no? And that is why if you observe, no, kunwari, if you have a faucet to, no, pangit yung drawing ko, pero this is a faucet, kunwari, if you notice a faucet, yung natural tendency ng water is to form a parang ganitong shape, tama? And this shape actually follows this equation, no? AT is equal to AC or ganyan. So that is why yung down sprues natin, usually we want it to be tapered in this manner, no? Pero obviously it's difficult to parang gagawa pa tayo ng parabolic na na taper. So ang ginagawa to estimate this parabolic taper, ginagawa lang nila is they just do a straight taper na ganyan lang, which is a good approximation na rin, no, ng yung natural tendency of a liquid that is free flowing or free falling from a certain height. Okay? So ang kino-compute lang natin again is AT and AC, and from here pwede na tayo through geometry lang, no? We can do we can already compute for the degree of tapering, which is just or something or commonly known as the taper angle, no? So we can compute for the taper angle just by kunin lang natin tong dimension na to, and through simple geometry mapasolve na natin yung taper angle, no? Or if you want the easier way, you can actually search for sa internet lang, just Google taper angle calculator, tapos meron doon ipapa-input lang sa iyo yung the big area, input lang yung big area, input lang yung small area, tapos input yung distance, kung saan distance between the big and the small area. Input nyo lang yung 3 values, you click calculate, tapos ibibigay na sa iyo yung taper angle. So you can also do that, no? Pero if you want a more rigorous na solution, you can calculate this on your own, no? Using geometry lang. Okay? Okay. So after that, we have your gating ratios, no? So I mentioned this earlier, yung gating ratio. So again, the gating ratio is just the area ng choke to the area of the runner, and again this is total area, no? And the total area of the in-gates as well. Okay? So the gating ratio actually has a big impact on how you intend to deliver your metal, no? So I've already mentioned this a while ago, and from here we can actually note if a system is a pressurized gating system or if it's an unpressurized gating system. Okay, so if the area is increasing, so from choke area to the in-gates, if it's increasing in value, therefore parang we are saying na we are relieving pressure, tama? Kasi if you think about it, kunwari sa choke area sobrang liit niya, tapos once it leaves the choke area, biglang maluwag na dito. Kunwari ganyan. Yung runner, kunwari ito yung choke area, no? It enters then into the runners, and the runners has a larger diameter than the choke area. And therefore dito, hindi na masyadong pressurized yung system mo, no? And this is what we call as an unpressurized gating system. Okay? Kung if it progresses, as it progresses, nag-i-increase siya, then you are unpressurizing it. The opposite is true if, for example, malaki yung choke area, tapos biglang pagpasok niya sa runner, mas konti na siya, yung choke area mo. Or mas maliit na yung choke area mo. So, kung mas maliit yung choke area mo, because, mas maliit yung runner area mo, meron tayong tinatawag na choke effect, no? We call it as the choke effect. And this choke effect introduces pressure in your gating system. So magkakaroon ka ng pressurized na gating system. And there are advantages and disadvantages to a pressurized versus an unpressurized gating system. And some of the advantages are kung pressurized siya, yung na-minimize yung tendency to have air aspirations, no? Kasi since pressurized nga siya, therefore hindi ka makaka-entrain ng mga gases, which prevents porosity. Tapos kung kung meron kang pressurized system, because of the added pressure doon sa liquid natin, yung gates natin, so if this is the runner, kunwari, ito siya, runner siya dyan, tapos it has multiple in gates. Because there is pressure in your system, then ang tendency is equal yung magiging flow rate from all of the three gates. Tama? Kasi may pressure eh. So just think of it as, kunwari, kung mataas yung pressure ng tubig sa bahay nyo, yung gripo on sa kitchen, equal lang yung flow rate niya if bubuksan mo rin yung gripo doon sa bathroom nyo, kunwari. Parang ganun. Pwede natin isipin na ganun. Dahil yun sa pressurized yung system. Now, think of the case wherein meron tayong unpressurized system. So, kung unpressurized siya, posible na yung pressure dito is malaki. Kunwari, dito nanggagaling siya, no? At dito galing yung choke area natin. So, nandito somewhere choke area. Papasok siya dito sa runner. Ito yung gates natin. Kung unpressurized yung system natin, then dito sa area na to, sobrang liit. Sobrang laki ng malaki yung pressure pa. Pero pagdating siya dito at dito, humina na yung pressure. Therefore, yung gates na to, unequal yung volumetric flow rate niya. So, kung unequal yung volumetric flow rate, posible na magkakaroon tayo ng defects, no? Kunwari, pwede tayo magkaroon ng incomplete casting. Kunwari, if this is the casting, may 3 gates tayo. Tapos, nag-miscalculate tayo, no? Hindi enough yung pressure, kunwari, posible na ang final casting natin will look something like, pwedeng ganito yung final casting natin, no? So, incomplete siya. Merong area dito na hindi na fill out dahil kulang na yung pressure sa point na to. Okay? So, you might see na parang sobrang daming advantages pala ng pressurized gating system, pero ang isa sa downside of a pressurized gating system is dahil pressurized siya, sobrang severe ng turbulences na na-experience ng material natin or ng mold natin. So because of the turbulence, posible na masira yung mold wall, tapos you can't cast properly yung final casting mo. So if you want better laminar flow, unpressurized system is the way to go, no? And in fact, in most cases, we want to do unpressurized gating systems. Okay, so from practice, we have this guide, no? So this is from several years of doing different gating ratios for different types of material, and we can use this as a guide, no? So for example, if we are doing aluminum kunwari, then we can choose this already established na gating ratios, no? We know that if we use these gating ratios, we usually produce a sound casting. So we have 1:2:1. This is a type of, and if I were to ask you, ano to? Is this pressurized or unpressurized? 1:2:1. Tawag ako ng isa, no? Ivana, what do you think? Pressurized ba siya or unpressurized? Kung 1:2:1. Diyan ka ba, Ivana? Baka nawala si Ivana. Si Rebo, what do you think, Rebo? Kung 1:2:1, do you think is it a pressurized or unpressurized type of gating system? Unpressurized. You would think pwede siya, no, na you might think na unpressurized siya, pero actually yung pinaka-importante when we talk about gating ratios is yung dulo, no, etong part na to. Kasi if you look at this, lumit yung area natin. So in that sense, actually pressurized gating system to. Kasi again, note that etong last kasi na value na to, etong last value na to, siya yung in-gate. Tama? So, yung in-gate mismo yung pumapasok sa ano natin sa mold cavity. So, yung in-gate is the more important na value to look at when we talk about pressurized and unpressurized system. Pero kung equal siya, what do you think? If it's equal, kung equal siya, then we need to look at kung ano yung pinanggalingan niya. So, for example, if it's, kunwari, 1:4:4, then obviously it's an unpressurized, no? Kasi galing sa 1, naging 4 siya. But if you look at, kunwari, 5:3:3, kunwari lang may ganito, no? Gating ratio, 5:3:3, then this is obviously pressurized, no? Parang ganun. Okay, so that can be something that you can take into account, no? So for example, if you have a sample problem or sa exams natin, kunwari, sabi na choose a gating ratio that is pressurized. Then you look at your, kunwari listahan, kunwari itong copper. Tingnan yung copper, which is pressurized. Both are pressurized, so you can use either, no? Parang ganun. So that is one way that we can transform the questions, no? Okay? So, other considerations for gating design is yung geometry, no? So, if we have a rangy casting or plate-like casting, rangy means, again, plate-like. We require multiple in-gates, no, to ensure that they are completely filled. Pero kung blocky yung casting, a blocky casting only requires kahit one in-gate sufficient na yun. Okay? Tapos, if we take into account the purity of the metal, kailangan din natin we need to take into account na yung purity of the metal will dictate kung top in gate siya or bottom in gate. So the top in gate and bottom in gate system is something like this, no? So for example, if this is the cross-sectional area of the runner, para ganyan, this is the again cross-sectional area ng runner to, no? And this is the in gate. This is what we call as a top in gate. Tapos bottom in gate is just the opposite, no? Bottom in gate is if we have parang ganyan. So, okay? So, ang difference niya is we usually want a top in gate. A top in gate will trap your or a bottom in gate is necessary para kung gusto natin mag-trap ng impurity. So again, ang sabi natin is impurities are usually lighter, so therefore kung nagpo-flow na yung metal natin and it has impurities, ito yung metal, nandito yung impurity natin. So because we have a bottom in gate, dito papasok, ang pumapasok lang actually yung pure metal lang, yung clean metal, so as to speak, no. So clean metal is going in and the impure metals are being trapped at the top portion. So this is a sort of this is the trap, no. Okay? So bottom in gates are needed pagka meron tayong lots of impurities, lalo na pag lighter yung impurities, no, like dross or junk. Tapos we can also use yung sinabi ko kanina, which is the runner trap, no, yung or runner extension. So the runner extension, sometimes ang runner extension is also known as the runner well, no. So runner well is provided at the end of the runner to collect the first metal, and ito yung sinabi ko kanina, the first metal is almost always the metal with the highest amounts of impurities. Okay? So, this is our last problem and siguro mag-extend tayo ng konti guys, no? Kahit 5 minutes lang. So, eto, we want to design a gating system for a 30 by 15 by 3.5 inch casting. And this particular casting will require 2 risers and an end chill. Okay? So, here are the given values. Gray cast iron na gagamitin natin. Fluidity of 35. And itong 35 na to, this is in inches siguro to. Wait lang ah. Okay ito. Nope. Okay. Okay. It's in inches, no? Ito, fluidity, this is in inches. Fluidity is in inches. Tapos, top gating system tayo. And a sprue height of 250 millimeters daw. Okay? Tapos, type of gating natin is a tapered choke sprue with 2 runners and multiple ingates. And it is noted na we are not doing bends in the runners, no? So our gating ratio of choice is 1:4:4, and we have a riser dimension with radius 4.617 inches and a height of 9.234 inches. Okay? The metal this has two values, no? Itong method, meron tayong solid density, meron din tayong liquid density. Okay, so first we need to determine the weight of the casting, and the weight of the casting is just equal to the volume of the casting. So ang assumption dito is yung volume na to, this volume is the final na volume ng casting natin, and well, taking into account na yung doon sa pattern makers allowance, doon sa pag-generate natin ng mold cavity. Okay? So if this is the final volume of the casting, then therefore ang i-multiply natin na density should be the solid na density, no? Tama? So, we need that's why ang ginamit dito is 0.255. So, notice na yung solid yung ginamit niya because when we are talking about the total solidification time, ang ginagamit natin is kung ano yung total weight ng gusto nating final product. So, since it's a final product, yung solid yung gagamitin nating value. So, notice that we are taking into account the volume of not only the casting, the final product, pero tinitake into account din natin yung riser, no? And in fact, if we want to be more accurate, kailangan din natin i-take into account yung gating system. Pero this is good enough na, no? So, again, for casting design kasi it's not necessarily an exact science, no? Posibleng in most cases medyo inexact lang siya. We are assuming certain values, and that assumptions are educated assumptions, no, based on the knowledge we have. So in this case, kahit hindi natin i-account yung gating system, enough na to na na assumption, because we know that the gating system as compared to the riser and the total casting is insignificant, no? So negligible siya as compared to these two values. So kaya okay lang gawin natin to. So we have riser plus the volume of the casting. We now have the total volume, and if we multiply that total volume with the density, the solid density, then we get the total weight of the casting plus the riser. So we'll use this total weight dun sa pouring time equation natin. So given yung fluidity, so this is just 35/40, and let me just show you here. Tama? Sorry. 6. So ito siya, nandito na. So it's 35/40, this is the K, 0.95, tapos 3.5 is the apparent thickness, and it's given here, no? Sabi dito, sabi kasi na yung casting daw is 30 by 15 by 3.5. So the 3.5 here, this is your thickness, no? So input natin siya doon. So 3.5, and it's already in inches, so hindi natin i-convert. 0. This is a constant, and multiplied by the square root of weight in pounds, no? So, square root yung gamit natin because again, hindi naman tayo lumagpas sa yung limit which is 1,000. So again, pag GCI, if it's less than 1,000 square root, if it's between 1,000 and 10,000, then you use cube root. Tapos more than 10,000, you use fourth root or quadratic root. Okay, so we have 118 seconds. So this is a long casting process, no? You need 118 seconds para ma-totally fill yung ano mo. Okay, so from here we determine the choke area. This is top gating. So again, h is equal to small h is equal to just 250. And we are assuming na either walang pouring cup to or yung pouring cup height is already accounted for dito sa 250 na to. So from table 11.3 again, C is equal to 0.9 and we can look at the table, no? Where's the table? Sorry. Nasa ano pala yun? Part 1. Okay, I'm finding it hard to find the table, no? Pero yung table just indicates na, di ba, if you remember, meron to yung certain values na kunwari multiple ingates, ganito, yung ganyan. So, hinanap lang niya yung certain condition. Tapos, we note that for that particular condition, yung hydraulic efficiency factor is equal to 0.9. So, from there, 0.9, kaya na natin i-compute to. So, we have our values, no? Pounds, and we need to, if we want to have a, wait lang. Sobrang weirdo. Pwede palang, dapat ginamit na lang, sorry. Dapat pala ginamit ko na lang yung 0.234 dito, no? Kasi if you look at this, this is in pounds, so there is actually no need to convert this into kilograms, no? Tapos ginamit yung density in kilograms because the density was also given in pounds, no? Okay, so pwedeng hindi na necessary tong part na to. So instead of using 6.48, instead of using this 6.48, pwedeng gamitin mo na lang is etong pounds para makuha mo in okay. I now know bakit ginamit yung kilograms, no, para hindi ka na mag-convert from millimeters to pounds kasi dito gusto natin ang final answer will be in SI units, millimeter squared. So kaya pounds kinonvert muna natin into kilograms para pag divide with density, we get millimeter squared. And notice class dito, no, this is in millimeters. This is the liquid density. So again, dahil dun sa volumetric flow rate equation to essentially, then therefore dapat density ng liquid ginagamit natin. Okay? So density ng liquid 717, input the density, input the hydraulic efficiency factor, input the pouring time na na-compute natin. Tapos we have 2 times G, these are constant, times 250 because this is top gating. So our effective head height is just equal to the sprue height, which ang assumption is already includes the pouring pouring cup height. Okay? Now we need to determine the gating dimensions. Since the cross-sectional area from the gating ratio is 1:4:4, then the total runner area is just equal to this value, si choke area multiplied by 4, tapos the choke area also multiplied by 4 to get the in-gate total. Okay? So sabi kasi sa problem, we have 2 runners and 2 in-gates. Therefore, etong area na to, we divide this by 2 to get the individual runner dimension. And ito din, i-divide natin by 2 to get the individual gate dimension. So for example lang, ang binigay sa problem is 3 in-gates siya. Then we need to divide this by 3. Etong value na to, magiging 3 to. Tapos, sabi kasi, we can assume na square yung cross-sectional area, no? So, if square yung cross-sectional area, then we just divide it, we just get the square root to get the dimensions. So, yung ano natin, runners natin will have a cross-sectional area of 20.65 by 20.65. And if you want to make it easier for our pattern makers, no, or our casting personnel, so dapat gawin natin ng 21 by 21 lang para mas madali nilang magawa tong runners na to. So 21 by 21, tapos ito rin 21 by 21. Okay? So malinaw ba? Meron pang, are there any questions before we end this session? Go ahead, Rebo. Kung kailan siya pwedeng gamitin? Um, Usually, ginagamit siya pagka kunwari explicitly sinabi sa problem, no? Pero kung hindi naman tinanong sa problem na gagamitin mo yung loss coefficients, pwedeng gawin nyo na lang is hanapin nyo dun sa hydraulic efficiency factor table lang, yung C. There are also cases where, for example, it's a unique design, no, that entails several loss coefficients. Tapos, hindi siya, kumbaga, hindi siya makaka-capture doon sa binigay ng table. Then, baka in those cases, kailangan mo gumamit ng loss coefficients, yung mga K sub 1, K sub 2, etc. So, siguro gusto nyo ng example, no, kung paano gamitin yung mga loss coefficients kasi ang binigay ko lang mga examples is puro C, no? So, um, I can give few more examples. Pwede ako mag-add ng supplemental materials na lang. Dagdag ako ng examples of how to solve the hydraulic efficiency factor if we were to use the loss coefficients para mas ma-imagine nyo kung paano siya ginagamit. Ganun na lang. Pero did I answer your question, Rebo? Okay. Other questions? Meron ba tayong other questions, guys? Yes, John. Go. Nabigay na yung design problem, di ba? Ah, oo nga, no? Hmm, sige, I'll consult with Sir Jolo, no? Kasi ang pwede natin gawin is kung ano yung groupings ng casting, yun din yung groupings ng design problem. Pero sige. Ang pwede naming i-adjust, pwede kasing i-extend namin hanggang yung binigay ng UP, no, which is January something. Pwede nating i-extend na lang para more time sa inyo. Group group work nga pala yun, no? Hindi siya individual. Okay. Okay, sige. Other questions? Kahit hindi sa lesson today. By the way, kumusta ang natin, webinar? Okay, ano yung date para maghanap din ako ng audience for you guys? December 16. Okay, I'll inform i-inform ko yung ibang faculty members as well as the possible audience. So thank you, December 16. Okay, thank you for that. Meron ba tayong other questions? I-remind nyo na lang ako, guys, no, para thank you, Riquel, pa-email na lang. Tapos kung pwede, guys, just in case makalimutan ko yung yung supplemental na examples, just go ahead and remind me. Pwede nyo akong i-message dito sa classroom na pare, sir, kailan ba i-upload yung yung supplemental materials para matulungan kayo sa calculations. Okay? So I think mukhang wala na tayong any further questions, no? So with that, we can end the session, and thank you guys for coming today. And I'll see you. Kailan ko ba kayo next makikita? Last session na natin to, no? Last session na nga ba? Sa 16 we can meet, siguro we can have a meeting Thursday ulit next week just to iron out the details. Tsaka maybe I can ask one din, no, para if Nagkaroon ba kayo ng ano, review session with one for the first LE, long exam? Hindi na. Meron ba? Ay, wala. Sige. Pwede namang i-request ko kung gusto nyo, we can have some sort of review session sa Thursday siguro. Kasi essentially we are done with the topics, no? Tapos supplemental na lang lahat eh. Yung powder met will be supplemental material, si ano din, si metal joining as well as yung process integration tsaka EHS considerations. So essentially, topic wise, no, we are done with the semester. So pwede tayong sa December 10 we can have parang review na, ironing out the details for webinars. And if you have any further questions no doon sa ano natin, dito sa topics natin. Okay? Okay tayo? Okay, I think that's good, no? So since there are no more questions, thank you again. Thank you everyone for coming, and I'll see you next week.